Welcome to this lecture series in real analysis. In this lecture, we'll learn the change of variables formula for integration, and let us recall just one ingredient, which is the fundamental theorem of calculus. So if we have a differentiable function on a closed interval whose derivative is Riemann integrable, then the integral of the derivative is the total change that the function witnesses. The integrals of all the infinitesimal change is the total change. That's the t-shirt version. Alright, so let's move on. So I want to get out of way one thing. It was supposed to be an exercise, but let me state it as a lemma because it is a lemma. So fix two differentiable functions and assume their derivatives are continuous. This is not the most expensive hypothesis, I suppose, but let's assume that their derivatives are continuous. Then the integral of this funny thing is another funny thing. There are applications of this thing, but I don't want to get into it. Let me just hint at what is the proof. The proof is an immediate application of the fundamental theorem of algebra, along with the fact that the derivative of the product is the following. This is the chain rule for differentiation. And now, since both sides are Riemann integrable, well, these are Riemann integrable because we assumed continuity of the derivatives. And since this is Riemann integrable, being the sum of two Riemann integrable things, this is also Riemann integrable. And if we integrate both sides, when we integrate this guy from a to b by fundamental theorem of calculus, we will get this. Right, and the other two terms are, so when you integrate the first guy, you get this, and you integrate the second guy, you get that. And you just rearrange to the algebra basic and you get that. It's a very simple result. But it is useful if you want to compute things. Many times it can be used, but I don't want to get into those things, like how to compute too many things, although it is important, it has its own place. But as of now, I don't plan to. Perhaps I'll give more exercises later, I don't know. Anyway, so now let's move on to change of variables. So fix a differentiable function and assume its derivative is continuous. Again, it is not the most optimal hypothesis, I suppose, but let's keep it like that. So we have a differentiable function defined on a closed interval whose derivative is continuous. And its image will also be an interval by intermediate value theorem or whatever. It is also a closed interval, in fact. Anyway, so that's the image of phi. And now if we have any continuous function defined on this closed interval I, then this integral, it's a funny looking integral, but perhaps I'll say a few words about it. So this funny looking integral is this integral. And we are not demanding that phi is injective or anything. It is possible that phi a equals phi b, in which case this will necessarily be 0. Okay? So, yeah, so we want to understand this guy. And the emphasis here in this lecture would be on the intuition, as it always should be. And then we will look at formal details, but I will not be so concerned with formal details here. Usually I am very meticulous about them, but here I will be a little less careful, maybe, I don't know. So let's try to understand this geometrically or pictorially or visually. Okay, so first let us draw or look at the graph of phi. Suppose this is what phi looks like. Okay, it could be much more horrible, but for the sake of understanding, suppose this is what phi looks like. So this is the graph of phi. Right, and now what we have here is the composite of f with phi. So so once I have an entry here, let's call it little x, I feed it to phi, and then I want to feed this length to, or this value to f. Now if I draw f here, then how do I get this value going inside f? That would be painful. So we will just rotate the graph of f by 90 degrees to achieve that. Right, so this is 90 degree rotated version of the usual picture. This is the x-axis, that is the y-axis. You choose a point here, you get the value that the function takes at that point, right? So this is the 90-degree rotated picture. The point is that, why have I done it this way? Suppose I have x here. I take this length, this signed length. This is phi of x, right? I go horizontally. So this is phi of x. And now if I take this length, this signed length, this is f of phi of x. Right? So that's why I've done it this way. All right. Now we are concerned with this integration. So to do that, we will partition the domain of this guy. The domain of this guy is this closed interval a comma b. We will partition it sufficiently finely. So we have partitioned the domain, and let's, so the name of the parts is A0, A1, A2, and so on up until B. Let's say there are n parts. Let's say this is AN. Maybe I'll write it. Okay. And now correspondingly, we will see a partition of the domain of F. And there is a little catch there, but let's roll with it. So I have so far only considered up until this point the partition, because when you go to the right, you will see other set of horizontal lines. Let's disregard them for the moment. Let's just focus on this part. So we get this non-uniform partition of the domain of F. We chose a uniform partition of the domain of F. That is convenient. But since phi is not necessarily a linear map, the graph is not necessarily a straight line, so you get some squishing at various places. Okay, now let us try to understand this quantity. What is this quantity? What do we usually think of this integral as? We may think of that integral as approximated by the quantity on the right. So this is the value of the function at the point ai, and that we have multiplied with this length, right? That entry here, or that quantity here, is this length. That's how we think of integrals, right? Intuitively, that is what integrals are. This is the area under the curve of this function. Nowhere in this picture have we drawn the curve of this function, but still, once you have a sufficiently fine partition of the domain of this function, this is how we think of the integral. Approximately, this is what it is. If you choose a fine enough partition, this quantity will better and better approximate this quantity. Okay. So this is what we're concerned with. So first, let us try to understand the second part, this particular value. What is that value? So phi prime of ai is here. The derivative of phi at ai is this slope of this tangent, right? But that we approximate as the slope of this line segment. Those things are difficult to draw, but let me attempt. So we have this line segment there, and the slope of this line segment is what we will approximate in our minds, the derivative of phi at the point ai. Right, so slope of this is the derivative of phi at ai for us. And that has been multiplied with this length, meaning this horizontal thing, meaning this horizontal thing. So what is this number? This number is nothing but this vertical thing. Doesn't look good. Maybe I'll try this color. Yeah, this looks a little more visual, more clear. So this length, or this signed length, we should be careful. This could be a negative thing, right? This very well could be a negative thing, but for this part in the diagram, this is all positive. This is a positive thing. So this length over here is this quantity. And that we have multiplied with this, which means that, so the thing in solid here is this quantity, and this length is that quantity. What is their product? Their product is this area, right? So if you consider this sum up until here. I mean, you don't go all the way. These indices, they run all the way. But if you only go all the way up until here, not throughout, you will be summing up this rectangle and then that rectangle, then that rectangle. So let me draw that again. So you'll be summing up that rectangle, then that rectangle, then that rectangle, and so on. So what you will be counting is, or approximately counting, the area under this curve. But you have to go all the way through. You can't just stop in between. You are concerned with this entire integral. So when you are coming down here, you'll be subtracting out some of the things, because when you're coming down, this quantity will be negative. Everything else remains the same, so to say, but these quantities will be negative. So when you're coming down, you'll be subtracting off some parts. What parts? Up until whatever that value is. So that area under the curve, you'll be subtracting out. What you'll be left with, just this area. So only referring to the figure at hand, all of this will be approximating the area that I've shown here. Right? Because you'll be subtracting out the corresponding part to this, corresponding region to this. Right? And that is what? So if you draw those horizontal lines, this horizontal line is, the figure gets messed up, but what can I do? So this is what? This is phi of B, and this one is phi of A. And ultimately, you are only registering the area under the curve F for this interval, which is what is written over here. So that's the intuitive explanation of the change of variables formula. It's not anything out of the blue. All right. And here is the formal proof. So you define the function capital F with domain capital I. Remember, capital I is the image of the domain of phi under phi. So you define capital F in this fashion. All right. And then, as we saw in the previous lecture, this probably was called the second form of the fundamental theorem of calculus, that the derivative of f is same as little f. Okay. And now, by the chain rule of differentiation, this is same as, I mean, this is just an equality. There's no chain rule here, but chain rule is here. So the second step is chain rule. Right? F prime is f as we noticed here. So here we apply the chain rule, and now this integral is that integral, which by the fundamental theorem of calculus, so this is equal to that integral by the fundamental theorem of calculus, that is equal to this value, which is equal to that value. So the formal proof is very, very simple, and it is not, strictly speaking, a direct execution of the intuition that we showed, but if you worry about it a little bit, you will be able to see, even from here, the intuition will be justified. But anyway, whichever you like, I think it's good to have the intuitive picture in mind. And let us see just one small application, and after that, we will finish this lecture. So here is a very, very simple application. Some garbage is already present here when I was preparing it. So what is the application? We want to integrate this. Now we already know how to integrate it, because inside there is a polynomial. So we can integrate it without much fuss. But let's try to apply what we just learned. Right? So what we see is that if we differentiate, if we differentiate the thing outside, not outside, but in this bracket, we sort of get what is here. Right? So that kind of gives us a cue as to how to go about this integration. So let f be, how should I define it? So let's f be defined, we'll define f later, let phi be defined in this way. So phi goes from, what should I do? It should be from 0 to 2, I think. Yeah, that's what I want. So phi is defined from 0 to 2 with phi of x being x square plus 1. Okay. And what is f? F is defined as, so what is the image of this guy? The image of phi is, so the image of phi is the interval 1 comma 5. So I'll define f from 1 comma 5 to reals as the identity map. Yeah, so that's how I define f. But first we also observe before we apply our change of variables formula, this whole thing is nothing but half of twice of x dx. So why has that come about? Because now 2x is the derivative of phi. So maybe I'll switch the order here. So this is x square plus 1. This is 2x. And inside what we have is f of phi of x. And this is phi prime x dx. Phi prime x is 2x. And f of phi of x is that quantity. And therefore, this is equal to half of phi of 0 to phi of 2 of integral of f, which is just x. So this is equal to half x square by 2, 1 to 5, which is half 25 by 2 minus 1 by 2. Which is God knows what. This is equal to 6, I think. Yeah, hopefully my calculations are correct. So anyway, I hope I have illustrated the point. Many more complicated integrals can be dealt with using this idea. But to get to them, we need trigonometric functions, etc., which we haven't gotten into yet. At some point we will. I mean, that's very important, but not yet. We need to develop the, power series machinery before we get there. Alright, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.